In this figure, we'll briefly introduce the relationship between Ck and x omega as period n increases. That means, given a periodic sequence, when we analyze Ck and x omega, what happens? Well, you'll realize now that, well, when we have a periodic sequence, and in this example is period 8, the same sequence repeating at period 16. Well, the same as in the on period is the same, the off period is actually being lengthened. So what happened is that we see that as this period becomes larger and larger, the on period remaining the same, there's some interesting relationship between Ck's and x of omega. This on the right hand side shows the frequency representation for different n. And remember that in the frequency representation, the x-axis is from 0 to 2 pi. So all this is from 0 to 2 pi. And what is this red line? This red line is x of omega. So x of omega don't change, because x of omega is simply this signal with all zeros on the right hand side as well as all zeros on the left hand side. So this is for x of n that is aperiodic. Now you see that as we are stretching our periodic signal with more and more zeros, doesn't this signal approaches x of n, and in the infinity they becomes the same. So there must be a very close relationship from the Ck's calculated to x of omega. So this is the figure. Well, on the right we are plotting x of omega, but we are plotting not only absolute of Ck, but we are plotting absolute of Ck multiplied by n. Why is this so? Let's see the equation. Let's see the analysis equation. This is the equation that we are interested in, which is the DTFS versus the DTFT. Notice that if in our example only from 0 to 3 is the xn non-zero, all ones. But notice this as well. Isn't this exactly the same as this equation? 0 to 3, that is non-zero. The only difference is 1 over n here. So once we multiply n by Ck, then this 1 over n is gone. Therefore, this equation and this equation will result in the same value once omega is the same. So with this insight, let us now look at our plot of x omega versus Ck. So we are plotting n times Ck. And if you notice, when we plot n times Ck, we're plotting all these blue lines over here. And for k equals to 8, you'll notice that there are 8 lines. So C0, C1, C2, C3, C4, C5, C6, C7, and of course when we reach 2 pi is C8. When we have n equals to 16, then the number of lines doubles from 8 to 16. C0, C1, C2, C3, C4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and if we reach here, it will be 16. And as we increase n to 24, we have even more lines. And when n equals to 2, even more lines. And then as we go from n to infinity, the lines will merge and it will form the continuum. Remember here we are plotting n times Ck. So this example clearly shows that in a periodic sequence, as n increases, then it will become the discrete time Fourier transform of the aperiodic sequence. Of course, it must be n times Ck for the relationship. We'll examine this further in the future. Right, so this concludes this chapter of 6.1. We have overviewed 4 types of Fourier analysis and synthesis. We have showed DTFS of periodic signal, DTFT of periodic signal, DTFT of aperiodic signal. We have also shown why it is called frequency representation. We have And more importantly, we have also visualized this complex exponential rotating, and we've seen the last slide, the relationship between nck and x of omega as the n-periodic sample becomes aperiodic as n goes to infinity. Thank you.